My name is Safiullah Said from EC second year. In this video I am going to explain about the characteristics and applications of an operational amplifier. The basic job of an amplifier is to amplify the input signal. Now we will see why it is known as operational amplifier. In the early days when the digital computers were not evolved at that time, the different mathematical functions such as addition, subtraction, integration and differentiation were performed using this operational amplifier. So just by connecting few resistors and capacitors, it is possible to perform different mathematical functions. This is why this amplifier is known as operational amplifier. So if we see the basic symbol of an operational amplifier, it has two inputs and a single output. Most of the amplifier runs on two supplies, the positive and negative, but there are some operational amplifier ICs which runs on the single supply. So now in this operational amplifier, the input terminal which is positive is known as non-inverting terminal, and the another input terminal which is negative is known as inverting terminal. So if you see this operational amplifier, it is one kind of differential amplifier with a single output. It means that this amplifier amplifies the difference between the two inputs. V1 and V2 are the input signals which are applied to this operational amplifier, and let's say the gain of this operational amplifier is A, then the output will be equals to A times V1 minus V2. So let's see, if we apply a single input to this operational amplifier and we have grounded the another input signal, we get A times V1, where A is the open loop gain of this amplifier. The reason it is called as open loop gain is because it is the gain operational amplifier when there is no feedback from output to input. If you give sinusoidal wave at the input, then at the output the sinusoidal wave is multiplied by this gain factor and we get amplified sinusoidal signal. Now here the phase of the output voltage is same as the input voltage. Likewise, if we are applying input to the negative terminal and we are grounding the another terminal, then the output of the amplifier is equal to minus A times V2, because the difference between the inputs is 0 minus V2, which is equal to minus V2. If we apply input as sinusoidal wave, then we have output as amplified sinusoidal wave which has 180 degree phase with respect to input signal. That means the output will get inverted by 180 degree. That is why this input terminal is known as inverting terminal. So now here, if we apply the input signal between these two terminals at the output, we get this A times differential signal. Now this operational amplifier is a high gain amplifier. The value of gain is used to be in the range of 10 to the power 5 to 10 to the power 6. So let's say if we apply 1 millivolts between the two terminals and this gain is equals to 10 to the power 5, and at the output theoretically we should get 1 millivolts into 10 to the power 5, that is equals to 100 volts. Or let's say we apply 1 volt, theoretically we get 10 to the power 5 volts, but that is not possible and the output of this operational amplifier is restricted between the biasing voltages that is being applied to this operational amplifier. So the output voltage will be between the biasing voltages. If you see the voltage transfer curves, it looks like this. Here the x-axis represents the differential input and y-axis represents the output voltage of the amplifier. The slope basically represents the gain of the amplifier. As we increase these values of input signal, then you will find that after some value of the input signal, the output gets saturated to the value positive Vset, which is less than the plus positive biasing supply. Same is for negative input voltages. So whenever this operational amplifier is used in an open loop configuration, at the same time Even if we apply small input signal, then also you will find that output will get saturated towards the positive or the negative biasing voltages. So this characteristic of an operational amplifier is practically useful as a comparator. So this is one of the application of this operational amplifier. The operational amplifier can be used in many applications like in active filters, oscillators, waveform converters, analog to digital converters and digital to analog converters, and it can be used in integrator and as an differentiator. So basically this op amp is very versatile IC, and you will find this operational amplifier in so many applications. The reason it can be used in so many applications is because of its different characteristics. Let us see the equivalent circuit of operational amplifier. It can be seen here the input impedance Ri in this operational amplifier. Likewise, this R0 is the output impedance of this operational amplifier. So the output of this operational amplifier is equal to the open loop gain multiplied by the difference between the inputs V1 and V2. Let us see the different characteristics of op amp. So the ideal operational amplifier should have the input impedance is equal to infinity, so that whatever input that is being applied at the input terminals will directly get applied to the op amp. Similarly, the output impedance of this operational amplifier should be equals to 0. That means whenever we are applying the output load, then the output voltage should directly come across the output load. If you see, the bandwidth of the ideal operational amplifier should be equal to infinity. It means it should support all the frequencies from 0 Hz to the infinity. Similarly, the gain of the ideal operational amplifier should be equal to infinity. Apart from that, whenever these two input terminals is 0, that means the output of this operational amplifier should be 0. Apart from this, there are few more characteristics, that is slew rate and common mode rejection ratio. So basically the slew rate is how fast the operational amplifier is able to reach its final value. In an ideal operational amplifier, the slew rate should be equals to infinity. It is defined in the unit of volts per microseconds. Then there is another mode known as common mode rejection ratio. Let us understand what this common mode rejection ratio is. So let us say we are applying some input voltage, then the difference between them is 0, and at the output we should get 0 volts. Likewise, when we are applying different input voltages to V1 and V2, then at the output the difference between the two voltages will get amplified by certain amplifier gain. So this common mode rejection ratio defines how well it rejects the common voltages supplied and how well it is able to amplifies the difference between the two voltages. It is basically defined as the ratio of differential gain by common gain. So in an ideal operational amplifier, the value of this common mode rejection ratio is equals to infinity. So till now we have seen these characteristics of an op amp. Input impedance should be equals to infinite, output impedance should be equals to 0, open loop gain should be equals to infinite. If input voltage is equals to 0, then output voltage will also be equals to 0. Infinite bandwidth and slew rate, infinite common mode rejection ratio. Thank you.